For nearly a century, physics has been split down the middle. On one side, we have the smooth, predictable rules of gravity that govern stars and planets. On the other side, the chaotic, probabilistic leaps of quantum mechanics. Mathematically, these two rulebooks refuse to talk to each other. To maintain the current consensus, the lambda CDM model relies on a series of unproven patches. It requires a sudden burst of exponential inflation and a constant dark energy to explain how an infinitely dense point became a uniform universe, theoretical fixes that effectively mask the singularity problem. In early 2026, a theoretical framework called infinite fractal descent offered an alternative. This model replaces the acausal Big Bang with a recursive hierarchy of structures endlessly nested inside one another, framing the universe as an infinite, self-consuming fractal. Cosmology's current impasse suggests a failure of geometric perspective. We have been trying to comprehend the mechanics of an infinite nested fractal by staring at a single theoretical dot. The James Webb Space Telescope recently sent back a curious anomaly. The vast majority of the earliest galaxies we can observe appear to be rotating along a preferred, shared axis. The infinite fractal descent theory provides a mechanical reason for this alignment. Our universe inherited its spin from a parent black hole, a higher-scale structure that actively ingested the material forming our space. Under extreme space-time torsion, the matter inside this parent black hole reaches a density limit. Instead of crushing into a singularity, the precursor mass hits a recursive instability point and instantly shatters into a uniform grid of smaller, self-similar nodes. The Big Bang was effectively a big bounce. Because this precursor structure was a fractal, the fracture happens everywhere at once. The resulting pieces settle into a smooth, flat mesh, which accounts for the uniformity of the cosmic microwave background, the thermal radiation left over from the early universe, without needing an imaginary inflationary field. We exist within the interior exhaust of a massive, spinning engine operating one scale up. If we descend from the parent scale down into our own observable universe, scale n, we can see this exact same process repeating. Supermassive black holes function as active computational refineries. During the macro input phase, black holes ingest stars and gas. As this matter compresses, it hits the absolute limit of space-time torsion. This repulsive force prevents a singularity, and the incoming matter is violently stretched and fractured into high-frequency wave states. At this density, the historical and structural data of a star is physically overwritten. This process follows Landauer's principle, the concept from thermodynamics stating that the logical erasure of information requires a physical release of energy. The complex data of a star is wiped clean. Quantum randomness is the literal thermodynamic heat and mechanical noise generated by this massive erasure operation. The fuzzy, uncertain world of quantum mechanics is the natural result of organized stellar matter being ground down into raw, unformatted data. As we follow this raw data down past intermediate ghost particles, we reach the final stage of refinement at scale n-1. This is the microscopic exhaust constantly being exhaled by the black hole refineries. Superfluid vacuum theory defines the vacuum of space as a dense physical liquid. Specifically, it acts as a tightly packed Bose-Einstein condensate, where individual particles blur into a single quantum entity. Solid matter interacts with this fluid constantly. Elementary particles acquire mass and create localized gravitational pull by displacing this dense liquid. Because the vacuum itself has mass and fluid dynamics, it exerts its own gravitational influence. This built-in density accounts for the high speeds of outer galactic rotation, removing the need to invent invisible dark matter. The expanding universe is physically filling up with a manufactured liquid substrate, continuously pumped out by the black holes of our scale. Pushing down to the absolute microscopic limit reveals a mechanical ceiling. As black holes exhale new spatial fluid, the older vacuum subparticles are pushed outward and subjected to fundamental tension. These subparticles are pulled like microscopic rubber bands until they hit a strict structural threshold and violently snap, disintegrating into the next smaller dimensional scale. Each tiny disintegration releases a burst of kinetic energy and rotational pressure. Multiplied across trillions of subparticles, this outward pressure drives the accelerating expansion of space. This mechanical fracturing is the physical reality behind dark energy. In early 2026, physicist Henry Tai at Cornell University calculated the limits of this process, mapping a definitive timeline for our cosmic expansion cycle. At approximately 25 billion years, the tension of our disintegrating vacuum will balance with the mass intake rate of our parent black hole. The expansion of space will stop, followed by the entire substrate collapsing backward into a single point, triggering a massive Big Crunch. The outward stretch of our cosmos is a temporary mechanical phase in a closed-loop engine with a definitive expiration date. Treating the vacuum as a physical, destructible fluid makes the direct manipulation of spacetime a matter of engineering. This is the basis for the scale resonance drive. Instead of exotic matter, the drive manipulates fundamental tension. By broadcasting precise, high-frequency radio spikes backward, it over-tensions the vacuum fluid, forcing subparticles behind the craft to shatter. This disintegration creates an expanding wake, an asymmetric pressure bubble shoving spacetime forward faster than light. From the parent black hole that birthed us to the quantum exhaust that fills our space, reality operates as an infinite, self-consuming fractal machine. Every scale feeds the next, and no matter how far down we look, there will always be a smaller sphere left to explore.